In this section, we are going to be looking at some properties of logarithms. The first property we are going to look at is called the product rule. The second property is the quotient rule. The third property is the power rule. Then we will use these three properties to first expand logarithmic expressions. Then we'll use these three properties to condense logarithmic expressions. And then we'll get the change of base property, and we'll use that to find a logarithm of a base other than base 10 or base e. Those are the two bases that you have on your calculator. LOG on your calculator is log base 10, and LN on your calculator is log base e. The first property that we get is called the product rule. Let B, M, and N be positive real numbers, and again the base cannot equal the number 1. The log base B of the product of M and N, so the log base B of M times N, is equal to the log base B of M plus the log base B of N. So the logarithm of a product can be written as the sum of the logarithms. Let's look at some examples. So let's use the product rule to expand these two logarithmic expressions. The first expression we have is log base 6 of 7 times 11. Using the product rule, we can write the logarithm of this product as the sum of the two logarithms. So we can write this as log base 6, and recall the base is written as a subscript, so it's to the right and slightly below the word log. So we have log base 6 of 7 plus the log base 6 of 11. So we can write the log of a product. A product is things being multiplied together as the sum of logs. All right, so the second logarithmic expression, the log of 100x, as you know, 100x means that you're multiplying 100 times the variable x. So we can write the logarithm of this product as the sum of the logs. So we can write this as the log of 100 plus the log of x. When you have a logarithm written as log with no subscript, this is the common log. So this is the logarithm base 10. So we are able then to simplify the expression log 100. Recall from section 4.2 that the logarithm is defined to be the exponent you raise the base to get the value that you're taking the log of. So the log of 100 would be the exponent that you would raise the base 10 to get 100. So log 100 would be 2, because to get 100, you would raise the base 10 to the second power. So we can write this as 2 plus the log of x. The second rule that we have for logarithms is the quotient rule. Let b, m, and n be positive real numbers with b cannot equal 1. Then the log base b of m divided by n is equal to the log base b of m minus the log base b of n. In other words, the logarithm of a quotient is the difference of the logarithms. A quotient means you're dividing two things. So you're dividing m by n. The logarithm of that quotient, m divided by n, can be written as the difference of the two logarithms. So it's the log base b of the numerator of your quotient minus the log base b of your denominator, n. All right, let's look at a couple of examples. So the log base 8 of 23 divided by x, that is a quotient. So the quotient rule says that when I have the log of a quotient, I can write that as the difference of the two logarithms. So we can write this as log base 8 of 23 minus the log base 8 of x. And you could, especially at the end of the section, when we get the change of base property, you could find a decimal approximation to the log base 8 of 23. It's just a real number. However, log base 8 of x, we cannot do that because we don't know what x is. X is a variable in this expression. All right, now let's look at the next quotient. We have the natural logarithm of e to the 5th divided by 11. So we can write that as the difference of the two logarithms. So the log, excuse me, I was about to write log base e, which it is, but let's just write that as ln. ln, the natural log of e to the 5th, minus the natural log of 11. Now you can actually simplify the natural log of e to the 5th. Again, what is the logarithm? The logarithm is the exponent that you raise that base to get the value you're taking the logarithm of. So the natural log of e to the 5th is 5. Because what are you raising the base e to get e to the 5th? And the answer is 5. Now you could also find a decimal approximation to the natural log of 11 using your calculator, but we're going to leave this expression in its exact form. When we say that this is exact, we mean it is exact. We're not finding a decimal approximation to this. We're going to leave it as an exact value. All right, the next rule or property we have of logarithms is called the power rule. Let b and m be positive real numbers with, again, b cannot equal 1, and let p be any real number. So if I take the log base b of m to the p, I can actually take that exponent out of the logarithm and make it a factor in my expression. So I can take the p out of the exponent and bring it out as a factor in my logarithm. So the log base b of m to the p is equal to p times the log base b of m. In other words, the logarithm of a number with an exponent is the product of that exponent and the logarithm of that number. And this is an extremely handy rule to be able to use. Very useful property of logarithms. Let's do a couple of examples. So the log base 6 of 3 to the 9th. Using the power rule, I can take the exponent 9 out of the logarithm and make it a factor. So I can take that out of the logarithm and make it a factor. So I can write this as 9 times the log base 6 of 3. So an equivalent expression to log base 6 of 3 to the 9th is 9 times the log base 6 of 3. Let's look at the next expression. We have the natural log of the cube root of x. Now you can write roots as rational exponents. So you can actually write this as the natural log of x to the 1/3. The cube root of x and x to the 1/3 are equivalent expressions. Now that I have this written in terms of an exponent, I can bring that exponent out of the logarithm and make it a factor. So we could write this as 1/3 times the natural log of x. The last expression is the log of x plus 4 squared. You're taking the logarithm of the binomial x plus 4 raised to the 2nd power. So you can bring that exponent out of the logarithm and make it a factor. So you're going to get 2 times the log of x plus 4. And I do need to leave the x plus 4 in parentheses because I'm taking the logarithm of that entire expression. Now, there's a real temptation when you get the properties of logarithms to try to expand the log of a sum. So there's a real temptation to want to do something with the log of x plus 4. And there is nothing you can do there. You cannot expand that logarithm. The only thing that you could do is know what x is, add 4 to it, take the logarithm of that, and multiply the result by 2. There is no expansion for the logarithm of a sum. There is only an expansion for the log of a product. You have the product rule, or the log of a quotient. You have the quotient rule, or taking the exponent out of a logarithm using the power rule. There is no property for the log of a sum. All right, so the properties for logarithms are the log base b of m times n is equivalent to the log base b of m plus the log base b of n. That's the product rule. The second property, the log base b of m divided by n is the log base b of m divided by the log base b of n. That's the quotient rule. The third property is the log base b of m to the p can be written as p times the log base b of n. That's the power rule. So now let's use these 3 properties, these 3 rules, to expand some logarithmic expressions. So the first one we're going to look at is the log base b of x to the 4th times the cube root of y. When using these 3 logarithmic properties to expand a logarithmic expression, you should use either the product rule or the quotient rule first if they apply. Then you would use the power rule last. So in this case, since we have the log base b of x to the fourth times the cube root of y, we're going to expand this first using the product rule. Product rule says that the logarithm of a product can be written as the sum of the two logarithms. So we can write this as the log base b of x to the fourth plus the log base b of the cube root of y. Now we're going to use the power rule to bring the exponents outside the logarithm and make them factors. So first of all, I'm going to rewrite my second logarithmic term as the log base b of y to the 1/3. The cube root of y and y to the 1/3 are equivalent. Now I can bring the exponent out of each of these terms as a factor times the logarithm. And I have my logarithmic expression completely expanded. All right, let's look at another example. Here we have a quotient. We have the log base 5 of the square root of x divided by 25 times y to the 3rd. And this one can be kind of tricky, so be really careful when you do your expansion. The first property we're going to use is the quotient rule. Since I have a quotient, I'm going to write this as the difference of the two logarithms. So this is going to be the log base 5 of my numerator, which is the square root of x, minus the log base 5 of 25 y to the 3rd. And I am taking the logarithm of that entire expression, 25y to the 3rd. So I'm going to go ahead and put that in parentheses so that I know that that's what I'm taking the log of. Now I probably would like to expand this a little further. I can certainly write the square root of x as x to the 1/2 power. So I'm going to do that. Maybe I'm going to do that. There we go. All right, so the second expression that I'm subtracting here, I can actually expand that also because it's a product. And so I'm going to do that. Now, since I'm subtracting that entire logarithm, I'm going to put the expansion of that inside brackets because I'm going to subtract everything, the entire log base 5 of 25 times y to the 3rd. Now, since that's a product, I can write that as the log base 5 of my first factor, 25, plus the log base 5 of y to the 3rd. Now I can do a little bit more. I can bring the 1/2 out, that exponent out of the logarithm and make it a factor. I'm going to leave this in brackets for now. The log base 5 of 25 actually has an integer value. What would you raise the number 5 to get 25? That's what the logarithm is. The logarithm is the exponent you raise the base to get the value that you're taking the log of. So 5 squared is 25. So the log base 5 of 25 is 2. And now on that second term inside my brackets, log base 5 of y to the third, I can bring the 3 out. All right, last but not least, I can remove the brackets by distributing the negative across each of the terms inside. And I have this logarithmic expression completely expanded. All right. You can also use these 3 properties to condense logarithms. So if you have, for example, the sum of 2 logs, you can write that as the log of the product. So you're using the product rule that we just got in reverse. So the log base b of m plus the log base b of n can be written as the log base b of m times n. You can also use the quotient rule to condense a logarithm. If you have the difference of 2 logarithms, you can write that as the logarithm of the quotient. So using the quotient rule in reverse. So the log base b of m minus the log base b of n can be written as the log base b of m divided by n. And last but not least, the power rule. If you have a factor outside of a logarithm, you can take that factor into the logarithm as an exponent on whatever you're taking the log of. So the power rule in reverse. So p times the log base b of m is equivalent to the log base b of m to the p. So now let's use these rules in reverse to condense a logarithmic expression. So we're going to condense these 3 logarithmic expressions. The first one we have is the log of 25 plus the log of 4. We can condense that logarithm because we have the sum of 2 logs. So I can write the sum of 2 logarithms as the logarithm of the product. So we could write this as the log of 25 times 4. And you notice I put the 25 times 4 inside parentheses so that I know I'm taking the logarithm of that product. 25 times 4 is 100. So this is equal to the log of 100. This is the common logarithm. Remember, if there's no base there, if it's written log with no subscript, that is the common logarithm, or log base 10. So what is that logarithm equivalent to? What would you raise a base of 10 to get 100? And you'd raise 10 to the second power to get 100. So the log of 100 is the number 2. All right, now let's look at the second expression. The second expression, we have the difference of 2 logarithms. I can write the difference of 2 logarithms as the logarithm of a quotient. So this is equivalent to the log of the first expression that I'm taking the log of, which is 7x plus 6, divided by the second expression that I'm taking the log of, which is x. And I would put that in parentheses so that I know that I'm taking the logarithm of that entire expression. Now you know how to evaluate an expression. For a particular x, you would substitute that value in for your x. You would find the quotient, and then you could take the logarithm of that quotient. So I need to put that in parentheses so I know I'm taking the logarithm of that entire expression. All right, the last one we have here, we have 2 times the natural log of x plus 1/3 times the natural log of x plus 5. Now before, when we were using these properties to expand a logarithm, we used either the product rule or the quotient rule first, and then we used the power rule. Since we're taking a logarithmic expression and we're condensing it, we use the power rule first. So if I have a factor of my logarithm, I am going to take that into the logarithmic expression as an exponent. For example, I have 2 times the natural log of x. So I'm going to take that 2 inside the logarithmic expression as an exponent. So that's going to be the natural log of x squared. Now I'm going to do the same thing to the second expression. I'm going to take that 1/3 into the logarithm, and I'm going to make that an exponent. So I'm going to raise the entire x plus 5 to the 1/3 power. Now I can rewrite that as the cube root of x plus 5. All right, I'm not quite done yet, because now I have the sum of 2 logarithms. If I have the sum of 2 logarithms, I am able to write that as the logarithm of their product. So I could write this as the logarithm, and I'm going to open up some brackets here or parentheses so that I know I'm taking the logarithm of this entire expression. That expression will be x squared times the cube root of x plus 5. Using those brackets again just to make sure that I know that I'm taking the entire expression, I'm taking the log of that. So it's the logarithm of x squared times the cube root of x plus 5. All right, so our last topic in this section is the change of base property. As you are aware, on your calculator, you have 2 logarithmic functions. The first is the common logarithm, or log base 10. The LOG button on your calculator is log base 10. You also have an LN button. That is the log base E. That is the natural log. So what if you want to find the logarithm of a base that isn't 10 or the base that isn't E? You have the change of base property. For any logarithmic bases A and B and any positive number m, the log base B of m is equivalent to the log base A of m divided by the log base A of B. So you can find the logarithm of any base by taking the log of m divided by the log of the base. Now we're going to use this with log base 10 and log base E. So you can find the log of any base of a number m by taking the common log of m divided by the common log of the base. Or you can use the natural log, and it's really up to you which one you want to use. They are the same value. The log base b of m is equal to the natural log of m divided by the natural log of b. You get exactly the same value, whether you use the common log or the natural log. Let's do an example. So let's find the log base 7 of 2,506. Now, what does the logarithm mean again? The log base 7 of 2,506 is the number that you would raise 7 to get 2,506. This is not going to be an integer. You're going to find a decimal approximation to this value. So to use the change of base formula, we take the common log of 2,506 and we divide it by the log of 7. And whatever decimal approximation you get there, that would be the log base 7 of 2,506. You could also use the natural log, and we're going to go to our calculator here shortly, and I'm going to show you that you get an equivalent value. You could use the natural log. So this would be the natural log of 2,506 divided by the natural log of 7. Whatever decimal of value you get for this, that's the approximate value that you'd raise 7 to get 2,506. So I'm going to share my calculator, and we're going to show you how to do this calculation. All right, so the first way we found the log base 7 of 2,506 was to use the common logarithm. So I'm going to take the log, LOG, right over here on the left-hand side of my calculator. I'm going to take the log of 2,506, and I must close my parentheses, must. And I'm going to divide that by the log of 7. Close my parentheses. All right, I'm going to hit enter, and I get 4.02 approximately. Okay, now let's do it using the natural log. So the natural log is right underneath my LOG button on my TI-84 calculator. So I'm going to take the natural log of 2,506, and I'm going to divide that by the natural log of 7. Make sure that I close my parentheses on both of those, hit the enter, and I get exactly the same value. So you can use the change of base formula to find the logarithm of any base by either taking the common log of that number divided by the common log of the base, or the natural log of the number divided by the natural log of the base. And that concludes section 4.3 on the properties of logarithms.